Annenberg Media.
Come on, let's get him.
Where's the pilot? I told him to meet me here. This can't be that hard. It's gotta be just like driving a car. Car's got a steering wheel, this thing's got a steering wheel. Car needs gas, this throttle will give you gas. Car's got a brake. Well, here's a brake. Does nothing.
You're the secret agent with the top secret package?
Shh. Uh-oh, better get in, here we come.
There he is. Let's get him.
That was me in my wild days. James Bond I was not, but I knew his secret. It's applying old skills to a new situation. I didn't know how to fly a plane, but my knowledge of how to drive a car enabled me to think about how I could fly a plane. To me, this is the key to algebra. As we tackle more and more complex problems, we should stop and think about what we already know. There's a good chance we can use the knowledge we already have to break down and solve a complicated problem. In previous programs, we've learned about exponents, we've learned about factoring, and we've learned about solving linear equations. In this program, we're going to bring all this knowledge together to solve a slightly more complicated equation, a quadratic equation. We'll learn that the key to solving quadratic equations is factoring. We'll see that the secret to factoring is to put the equation in a form we've seen before, called the difference of squares. And to help us put the equation in this form, we'll learn a technique called completing the square. Here's something that may look familiar. This is a polynomial of degree 2, but now it's an equation. And this equation has a special name. It's called a quadratic equation. The name comes from the Latin word quadrus, which means square. It's this square term that makes it a quadratic equation. Notice that the terms are written in descending orders of the power of the x term, and that the right side is equal to 0. This configuration is called the standard form. When we get a quadratic equation, we'll often find it helpful to put it in standard form. Now, we've been looking at a specific quadratic equation. Here's a general quadratic. It's ax squared plus bx plus c equals 0. We've replaced the specific coefficients with the letters a, b, and c. These represent real numbers. A can't be 0, or we get this, a linear equation. Remember, we must have a squared term to have a quadratic. If b is 0, we get this, still a quadratic. And if c is 0, we get this. Again, still a quadratic. Let's have a pop quiz to see if we can recognize quadratic equations. Is this a quadratic equation? No, it's a linear equation. It's not a quadratic equation since there's no squared term. Is this a quadratic? Yes, this is a quadratic equation. Now, don't be deceived because there's no middle term. It's not necessary for it to be a quadratic. Is this a quadratic equation? No, this is a picture of my father. Is this a quadratic? No, this is not a quadratic equation since there's a cubed term. Is this a quadratic? Yes, this is a quadratic equation. You may not recognize it because it's in Akkadian, the language of the ancient Babylonians. This is one of the oldest traces of the quadratic equation. It was written over 3,600 years ago on clay tablets known as cuneiforms. The Babylonians were using quadratics for practical purposes like commerce and engineering before the Greeks even had a language. Now that we're familiar with quadratic equations, let's take a look at a modern-day environmental problem, acid rain, and see how algebra and quadratic equations can really help.
A gentle rain on a New England lake, but not a beautiful picture. It's acid rain, and it's disrupting the chemical balance necessary for life. This lake used to be teeming with fish and plants. Because of acid rain, it's now practically barren. The cause is well known. Pollution from our automobiles and our power plants react in the atmosphere to form acids, which return with each rain. Scientists are now studying individual lakes. They assess the chemical damage by measuring the acidity, and they see its effects by monitoring the fish population. There's hope for counteracting the acidity with a chemical, lime. It's a bit like taking an antacid for an upset stomach.
Okay, I have a solution of an acid and a popular antacid tablet, which as an active ingredient is the same material as the lime that we add to a lake. And I'm going to add the tablet, and you will see the bubbles indicating the reaction is taking place. We are neutralizing the acid. You can think that lake liming is adding a giant antacid tablet to the water.
Except the antacid arrives in a truck and is applied with a helicopter. And the recommended dosage? Here they turn to algebra.
I don't think one could work in the liming lake business or any part of the aquatic environment without doing algebra. Algebra is exceedingly important to a chemist. We don't always just shake test tubes and mix things in beakers. We do that, and we make measurements on the big beaker like a lake. But ultimately, we have to do something with those data. And this means for the kind of work that I do, we do quite a bit of calculations, which are all algebraic computations.
Results show that liming works. Acidity returns to an acceptable level, which is good for the lake's inhabitants. But liming is a medicine that treats the symptoms, but does not cure the underlying problem. Every rainfall brings a painful reminder of this.
As we do in our own health, if we're not too well, we take some medicine, but we hope that that's short term, and eventually we can be healthy and maintain ourselves. And I would hope that the same thing is true here, and namely that we can reduce the amount of what I choose to call an insult to the lake, the acid falling into it.
Let's see how a quadratic equation arises from liming. I'll use a simplified example. Say I have an acid rain damaged lake and I want to add lime to neutralize the acid. In the lake, the acid and lime will combine to form a harmless compound called bicarbonate. The first thing I do is assess the lake. I find 2 units of acid and no units of bicarbonate. Now I'm going to add the lime. The reaction between lime and acid isn't very efficient. Not all of the acid and lime will react to form bicarbonate. So to use up as much of the acid as possible, I'm going to add a lot of lime. Let's say 5 units. Now let's think about what happens at the end of the reaction. Bicarbonate's been formed. We don't know how much, but we'll call the amount B. Now it's the nature of the reaction that for every B units of bicarbonate formed, B units of acid and B units of lime are used up. So I end up with 2 minus B units of acid and 5 minus B units of lime. Well, we can figure out how much bicarbonate is formed and how much acid is left. According to the rules of chemistry, the amount of acid at the end of the reaction 2 minus B, times the amount of lime at the end of the reaction, 5 minus B, equals the final amount of bicarbonate, B. Well, almost. As I said, our reaction is not very efficient. Not all the reactants react. So to account for this, we need to divide the product of the reactants by a constant K. In this case, let's say our constant is 4. Well, now we have an equation for the amount of bicarbonate formed, but it's not in a very convenient form. Let's remedy this. First, I'll multiply both sides of the equation by 4 to get rid of the fraction. Now I'll multiply the two binomials using the FOIL method. First, 2 times 5, which is 10. Outside, 2 times negative b, which is negative 2b. Then inside, negative b times 5 for negative 5b. And last, negative b times negative b, which is b squared. We'll combine negative 2b and negative 5b to get negative 7b. And this equals 4b. Do you recognize this? It's a quadratic equation. It will be clearer in standard form. First, we'll subtract 4b from both sides, making this side equal to 0. And on this side, we get negative 11b. And now we'll rearrange the order of the terms. Well, now that we have an equation, we have something we can actually solve. And solving this equation will tell us the final amount of bicarbonate and will allow us to figure out how much acid remains in the lake. We can then decide whether it's an acceptable amount or whether we need to add more lime. Well, we haven't solved quadratic equations before, but let's think through our arsenal of algebraic techniques. In a previous program, we learned about polynomials. We learned that they can be simplified by factoring. Now that we've advanced to equations, we'll see that they can actually be solved by factoring. Here's our quadratic equation. We're going to factor this into two binomials. The first term is b squared, so we'll put a b here and here. The last term is positive 10. Now, there are a number of ways to produce 10. To see which one, if any, will actually work, we need to look at the middle term, negative 11b. Negative 10 and negative 1 will work. So these are our factors. And don't forget this, equals 0. It's this equals 0 that's the key to solving quadratic equations. The only way the product of two expressions can equal 0 is when at least one of the expressions equals 0. This fact is so fundamental to algebra that it has a name. It's called the zero product property. Let's see how this works. Here's our factored equation. If b minus 10 is 0, we get 0 times b minus 1, which is 0. Or if we look again, and instead b minus 1 is 0, we get b minus 10 times 0, which is 0. So to find the solutions to our equation, all we have to do is figure out when each of the factors equals 0. We want to know when b minus 10 equals 0 and when b minus 1 equals 0. These are just two linear equations, and these we know how to solve. We'll add 10 to both sides and get b equals 10. And we'll add 1 to both sides. We get b equals 1. Notice that we get not one, but two solutions. This is always the case for quadratic equations. Two solutions means that there's twice as many answers to get wrong, so we better check our answers. Here's our original equation, b squared minus 11b plus 10 equals 0. Now, if we try b equals 10, we get 100 minus 110 plus 10 equals 0, which checks. If we try b equals 1, we get 1 minus 11 plus 10 equals 0, which also checks. So both of our answers are mathematically correct. Now we have to go back to our original situation and interpret our results. Remember, at the end of our liming, we had b units of bicarbonate formed, leaving 5 minus b units of lime and 2 minus b units of acid. If 10 units of bicarbonate formed, we're left with 5 minus 10, or negative 5 units of lime, and 2 minus 10, or negative 8 units of acid. Well, you can't have a negative amount of acid or lime. So while 10 makes sense as a mathematical solution to our equation, it does not make physical sense. When solving quadratic equations, it's not unusual to get one answer that's mathematically possible, but physically impossible. Let's look at our other answer. If 1 unit of bicarbonate is formed, we have 5 minus 1, or 4 units of lime left, and 2 minus 1, or 1 unit of acid left. These results do make physical sense, and they're good news as well. 1 unit of acid turns out to be an acceptable level. We've solved the quadratic and improved the lake, at least for the time being. Now, this is the first quadratic equation we've solved, so let's take a moment to review our steps. First, we put our equation into standard form. Second, we factor it into 2 binomials. Third, we use the zero product property, set each factor equal to 0, and solve. Fourth, we check both our answers. And finally, we interpret our answers in terms of the original problem. Now, these steps work pretty well, but we were lucky. We were able to factor our equation by trial and error. Unfortunately, very few quadratic equations can be factored this way. Well, what can we do? Once again, it's time to think of some of the techniques we've learned before. We've met a polynomial that always factors. It's the difference of squares. That's x squared minus y squared, and it factors as x plus y times x minus y. Well, what we want to do is to take our quadratic equation and put it into the form of the difference of squares. Once it's in that form, we can factor it and solve our equation. You know, I remember a time when the difference of squares really came in handy.
So what's it like being a secret agent?
Look, we got business to do. Any minute, we're going to see the secret target. We got to get this package into the right hands, if you know what I mean.
You know, if you drop it, it won't fall straight down because the plane is moving.
I got an equation that can help. Let's see, here's my binoculars, my mini recorder, my laser. You got a pen?
The pressure was on. I needed to find a pen, but more importantly, I needed to figure out at what point to drop the package from the plane so it would land on target. Here's what I did. I had a formula. D squared equals h times s squared, all divided by 16. Here, D is our desired drop point, the horizontal distance from the plane to the point directly above the target. H is the height of the plane, and s the speed of the plane. Well, we were going to drop it from a height of 50 feet and at a speed of 70 miles per hour, which is about 100 feet per second. I got d squared equals 31,250. I recognized it right away. A quadratic equation. I subtracted 31,250 from both sides to put it into standard form. And I looked closely and I said, this is actually the difference of squares. See, 31,250 is the same as the square root of 31,250 squared. So we have one term squared minus another term squared. And this factors as d plus the square root of 31,250 times d minus the square root of 31,250 equals 0. Once I factored it, I practically had it solved. Our equation equals 0 when either this factor equals 0 or this factor equals 0. I subtracted from both sides and got d equals negative the square root of 31,250, or about negative 177. And here I added to both sides and got d equals the square root of 31,250, or about 177. Well, d was the distance from the plane to the target, so I knew I wanted the positive solution. We were in a hurry. The target was rapidly approaching, and I could sense that the enemy was closing in on us. But as I said then, and I say now, there's always time to check your answer.
So we've got to drop it 177 feet from the target.
Did you check your answer?
Of course I checked my answer.
There's a target. Get ready. Drop it now.
Yes, way to go. We did it. All right. Bang.
Well, I made it look pretty easy. But sometimes, like here, the difference of squares isn't obvious. I'll subtract 16 from both sides. Recognize it? This is actually the difference of squares. 16 is 4 squared. And x squared plus 4x plus 4? This is the type of polynomial we've seen before. It's called a perfect square trinomial. And like the difference of squares, it always factors. Perfect square trinomials are in the form x squared plus 2xy plus y squared is equal to x plus y quantity squared, and x squared minus 2xy plus y squared, which factors as x minus y quantity squared. So, returning to our example, x squared plus 4x plus 4 factors as x plus 2 squared. Now we can see that we have one expression squared minus another expression squared equals 0. And this factors as x plus 2 plus 4 times x plus 2 minus 4 equals 0. To solve this, we just need to set each factor equal to 0 and solve for x. Now, our equation just happened to have a polynomial that was a perfect square trinomial. But that's not usually the case. For example, there was the time...
Look, there's your secret runway.
Where?
You just missed it.
Pretty short, eh? Think we can land?
I'll try to bring it in real slow, but too slow and I'll stall and end up in those trees.
Look, let's just ditch the plane. Hey, we got any parachutes back here?
I thought you were bringing the parachutes.
Stay calm, don't panic. What are we gonna do?
Hey, you're the mathematician.
Of course, algebra, equations.
Well, I didn't panic, and neither should you, because there's an equation that can help us. The equation is 0.1 times s squared minus 3s plus 22 equals d. Here s is the initial landing speed in feet per second, and d the stopping distance needed in feet. The runway looked about 500 feet long, so we'll replace d with 500. Now, solving this equation will give us s, the speed which will enable us to land a plane without going off the runway. This was something I was dying to find out. Let's go ahead and solve it. First, let's multiply both sides by 10. Now, it would be great if this were a perfect square trinomial, but unfortunately, it's not. But I'm going to show you a technique for making it one. It's called completing the square, and it'll work for any quadratic equation. The first step is to make sure the coefficient of the squared term is 1. We've already done this. Now we'll subtract 220 from both sides. This isolates the variable. Now we can think of these two terms as the first two terms of a perfect square trinomial. To get the third term, all we have to do is add the right number here. There's a handy rule that tells us the correct amount to add. We find the coefficient of the middle or linear term, here it's negative 30, take 1/2, which is negative 15, and square it and get 225. Adding 225 here makes this a perfect square. And if we add 225 to one side, we need to add 225 to this side, which makes this 5005. Now we can factor our perfect square. It's s minus 15 squared. We can subtract 5005 from both sides, and we can think of 5005 as the square root of 5005 squared. Now we have this squared minus this squared, which is the difference of squares. And now we can factor and solve. Completing the square is a powerful technique, and it makes sense. By adding the same thing to both sides, we're just putting our equation into a form that we know how to factor. It's an important technique, so let's review our steps. First, we make sure that the coefficient of our squared term is 1. Second, we isolate our variable. Third, we take 1/2 of the linear coefficient, square it, and add it to both sides. Fourth, we factor the perfect square trinomial we just made. And finally, we put our equation in the form of the difference of squares. Now let's go ahead and find our solutions. We have the difference of squares, and it factors as this. We get 0 when this factor equals 0, or this factor equals 0. The square root of 5005 is about 71, so we get s equals negative 56, and positive 86. Well, the speed needs to be positive. So in order to land the plane without going off the short runway, our initial landing speed needs to be about 86 feet per second, which is about 59 miles per hour. Well, there are two things I still don't know. I don't know if I made a mistake because I haven't checked my answer in the original equation. And I don't know if the plane will stall at 59 miles per hour. Well, I checked both in a slightly more dramatic way, by landing the plane.
So you need to go about 59 miles an hour.
Well, I think I can do it. You can open your eyes now.
Now, there was another way to solve this problem. It's called the quadratic formula. Here's the general quadratic equation. If you complete the square and solve for x, you get this famous formula. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. To use the formula, all we have to do is put the equation we're working with in standard form and substitute the coefficients for a, b, and c. As a mathematician, I prefer completing the square over using the quadratic formula. When I complete the square, I feel in control. I'm doing the mathematics, not just using a formula. Well, in my time, knowing how to solve quadratic equations has pulled me out of a few jams. You know, other secret agents are forced to do crazy stunts, like jumping out of planes right as they're about to crash. I never had to do stuff like that, and I'll tell you why. Whether I'm foiling an international spy ring or solving an algebra problem, I have a few skills. But most importantly, I know how to look at a new situation and apply the knowledge I already have.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.